This is 1.D.3 homework 7.16. The blue color of the sky results from the scattering of sunlight by air molecules. The blue light has a frequency of about 7.5 times 10 to the 14th hertz. Calculate the wavelength in nanometers associated with this radiation is letter A. So we're using the formula C equals lambda nu. C is the speed of light, nu is the frequency. If we rearrange it, we get lambda equals C over nu. Looking for wavelength. Speed of light is 3 times 10 to the 8th meters per second. Nu is 7.5 times 10 to the 14th. Seconds to the minus 1. And so that means seconds are going to cancel. Seconds cancel, we get meters for our answer. 3 times 10 to the 8th divided by 7.5 times 10 to the 14th is 4 times 10 to the minus 7. They're 10 to the 9th nanometers in a meter. So that's 4.0 times 10 to the 2 nanometers. The second part of the question says calculate the energy in joules of a single photon. So we use E equals h nu. H is 6.626 times 10 to the minus 34 joule seconds. Nu is 7.5 times 10 to the 14th hertz, or seconds to the minus 1. 6.626 times 10 to the minus 34 times 7.5 times 10 to the negative, or to the positive 14th is 4.97 times 10 to the minus 19 joules, or 5.0 times 10 to the minus 19 joules. Moving on to 7.18, it says what is a wavelength in nanometers of radiation that has an energy content of 1 times 10 to the 3rd kilojoules per mole? In which region of the electromagnetic spectrum is this radiation found? This question we need to convert from kilojoules per mole to joules per photon to get the wavelength. We always work from individual photons and their energies and frequencies in order to get wavelength, not kilojoules per mole. So we have 1,000 kilojoules per mole. There are 1,000 joules in a kilojoule, and there's 6.02 times 10 to the 23rd photons in a mole of photons. So multiplying by the top and dividing by 6.02 times 10 to the 23rd, remember to put that in parentheses, we get the energy is 1.7 times 10 to the minus 18 joules. Now we need to plug that into an equation that gives us wavelength. Remember, this is the combination of E equals h nu and C equals lambda nu. It's E equals hc over lambda. If we rearrange it, we get lambda equals hc over E. So plugging in our numbers, 6.626 times 10 to the minus 34 joule seconds, 3.00 times 10 to the 8th meters per second, and the energy of 1.7 times 10 to the minus 18 joules. Once again, remember to divide by putting it in parentheses. We get 1.2 times 10 to the minus 7 meters joules cancel, seconds cancel, times 10 to the 9th nanometers per meter. So that's 120 nanometers. 120 nanometers is smaller than 400 nanometers, and so that would put it in the, since 400 is violet, that would mean it is ultraviolet. Here's our final question, 7.32. Calculate the frequency in hertz and wavelength in nanometers of the emitted photon when an electron drops from the n equals 4 to the n equals 2 level in a hydrogen atom. So for 32, we were told to use the Bohr equation, which is the nth energy level has an energy of negative 2.18 times 10 to the minus 18 joules times 1 over n squared. So the fourth energy level would be negative 2.18 times 10 to the minus 18 joules times 1 over 4 squared. The second energy level would be that times 1 over 2 squared. So calculating those values quickly. We get 1.36 times 10 to the minus 19 joules. That's a negative. And 5.45 times 10 to the minus 19 joules, also negative. Now we are going to be taking the difference in those two numbers. And we get that the difference is negative 4.09 times 10 to the minus 19 joules. Now let's talk about the negative sign. The negative sign simply means that when the photon drops from 4 to 2, energy is lost by the atom. There's a photon that comes out of the atom. So the energy is negative because the atom is losing a photon. But the energy of the photon is positive because energy is a positive quantity. It's something that can't have negative. It can be assigned negative to an atom if something loses energy. But in this case, the 4.09 times 10 minus 19 joules, we should change the sign on that because we're now not considering the atom's energy, but rather the photon's energy. And now dividing both sides by h, 6.626 times 10 to the minus 34 joules seconds, we get the frequency. So 4.09 times 10 to the negative 19, and then divided by parentheses 6.626 times 10 to the negative 34, and we get 6.17, times 10 to the 14th seconds to the minus 1 is our frequency. Rearranging C equals lambda nu, the wavelength is going to be C over lambda, or 3 times 10 to the 8th meters per second over 6.17 times 10 to the 14th seconds to the minus 1. So the speed of light divided by the frequency comes out to 4.86 times 10 to the minus 7 meters. There's 10 to the 9th nanometers in a meter. So that would be 486 nanometers. So frequency 6.17 times 10 to the 14th per second, or hertz. And wavelength 486 nanometers.